It's a pleasure to be here. Thank you very much, Anne, for the introduction and for the invitation to speak to you. Um, I'm here on presenting the work on behalf of the team at Robinson. You can see a photo of the space team there, and I would like to talk about superconductors in space. And the very first thing I thought was, well, how is it related to astronomy? And yeah, I mean, there's not a huge overlap, but there's a few things there which I thought was quite fun. So I'll go into those examples and we'll see what we make of them. So as to these words, I'm sure people know most of them, but maybe not too much about this word here, superconductors. So let's kick off with a little bit about what they are. Okay, so it's a thing, it's a material, and one of the most sort of well-known things that it does is once you cool it down to a certain temperature, use a laser pointer, the electrical resistance falls to 0. And so if you take your ohm meter and you measure the resistance across your superconductor at a certain temperature, it's 0. The temperature is quite low. So, in this example, think, sort of minus whatever this, 180 degrees Celsius or something like that. Okay, so the other thing they do is they also expel a magnetic field, but that's not such a biggie. Okay, so the other way to answer the question, what is a superconductor? Well, actually, most things are a superconductor. Superconductors here is the periodic table of the element, and the ones colored in display superconductivity. There's also, you can mix elements together to make new compounds, and those can be superconducting. This chart here shows that temperature at which the resistance falls to 0, and that's shown on the axis up here, and then on the axis down here, it's showing the year in which the material was discovered. And so the one we work with mostly in Robinson, the one I'm going to talk about is this particular one here, and you can see it's a mix of various elements. So it's a relatively complicated material. And it's also quite a sort of complicated structure when you actually, buy the thing from this manufacturer. I keep forgetting to use the mouse. So the superconductor part is this little black bit here, and then to actually make something you can use in your magnet or your device, there's all of this other stuff which needs to be incorporated. This is now, it's a sophisticated but pretty mature technology. And recently, the price and availability of superconductors really come down mostly because people wanting to make fusion reactors have ordered a lot of tape, and so the production is really ramped up. So why are superconductors interesting? So, you can think 0 resistance, they're efficient, but the other thing is kind of how much current you can put through these things. So I've got a current density value here. This is an engineering current density. So this is everything, the entire tape, and you can put about 50,000 amps per square centimeter. So as an example, a square centimeter is about the cross section of your thumb. That's okay, I'm sorry, and that's it in minus 200 degrees Celsius. If you go down to closer to minus 270, it's a factor of, which is well achievable. It's a factor of 10 or 12 higher. The comparison is not quite. It's a little bit nuanced, but this is something like 1,000 times more current than you can get through copper. So that's roughly what superconductors kind of do, roughly. Why are they interesting and useful and for space? And so there are a couple of applications which I want to talk about. Firstly, I want to talk about something called sort of when you can make a cavity with a very high Q factor. That's if you want to kind of filter signals. The other one I think maybe is a bit more interesting is these so-called transition edge sensors. That is when if you want to see very low energy light, so you can use a superconductor as a detector. Another way of saying low energy light is very, very far infrared light. So you can use a superconductor as your sensing element. This little image down here is to remind me to say that superconductors have actually flown in space before. There's been one demonstration. It flew in the late 90s, and it basically demonstrated the superconducting material that we've been working with, that it basically remains superconducting in the environment of space. By far, though, the majority of applications involving superconductors in space, you wind the superconductor into a magnet, an electromagnet. So just very briefly, in case it's a bit unusual. So what do I mean by a magnet? So you take your superconductor or your wire or whatever, you wrap it in a coil, and if you put current through it, you generate a magnetic field. So the field, roughly goes as the number of turns you have in your coil times the amount of current going through it. And this is the way people make the most powerful magnets in the world. You don't make them out of a magnetic material, you make it an electromagnet. Here you can see an example of a 32 Tesla magnet. This is one of the most powerful magnets in the world at the moment. And it's made, of course, from superconductors. Okay, so that's what electromagnets are, and why you need to use a superconductor, so you can put a lot of current through them. And these are some of the applications for electromagnets. So firstly, as a component in a particle detector, I'll talk a little bit more about that later. There's radiation shielding. There's been a whole bunch of concepts around that. There's what I call sort of some neat experiments we've been working on, showing you can potentially use this as a heat shield for re-entry of a spacecraft to lower the thermal load on your spacecraft. Another one is attitude control. So that's if you want to rotate your spacecraft. You can basically push off the Earth's magnetic field. You can use the field generated by your coils to kind of rotate you and push the Earth field. And another one, which is very dear to my heart, is electromagnetic propulsion. So this is actually to propel your spacecraft. Okay, so I wanted to talk about basically these two, because this is where there's a little bit of overlap with astronomy, and I thought it'd be kind of fun to talk about it. And the first is a detector, which was the first is using superconductors and detectors, and I want to talk about the AMS 02, which was the superconductor magnet in space, which nearly was. It wasn't quite. So the AMS is a particle detector on the International Space Station. It's now been in operation for about 14 years. It is a precision and direction discriminated measurement of particle charge, energy, and momentum up to very high energies. So this is looking at cosmic rays coming from deep space. So it's to investigate those, search for antimatter and various other cool physics. So it relies on a powerful magnet, and it was almost going to be a low temperature superconducting magnet. They built the magnet, designed it. It would have given the instrument better performance, but right at the last moment, they decided it wouldn't allow the instrument to operate as long as they had wanted, for various reasons. And that's because to keep this superconductor cold, they need a lot of kind of liquid helium, a lot of cryogens that would have boiled off over time and wouldn't have given the lifespan they wanted for this particular instrument. That's part of the thing, a reason why the technology we're developing is interesting is because you can get away from these liquid cryogens, which limit your lifetime. Okay, and then the other kind of broad area of overlap with astronomy I wanted to mention was using superconductors in these propulsion systems for spacecraft, and particularly sort of obstinate spacecraft, which might be used for observing. And I wanted to pick a quite a sort of crazy example, but I thought it's quite fun. And that's this concept of using the sun as a gravitational the solar gravitational lens effect, and so basically using the sun as a giant telescope. So the attraction of this is that and theoretically you can image exoplanets. You can get astounding magnification from doing this, but there are some practical difficulties. And one of the many difficulties is that you actually need to position your telescope at 600 AU out from the sun. But generally, you need very good in-space propulsion systems to work with concepts like this. Some less sci-fi examples, if you want to observe at the Lagrange point, the JWST, or some other sort of advanced concepts where the positioning of your satellite, your observing telescope or your satellite is important. So this is where kind of I think we've kind of come in is looking at next generation improved spacecraft propulsion systems, and specifically how superconductors can do this. What's shown here is a test of our spacecraft thruster in our lab. You can see, well, okay, what can you see? So what we do is we feed in a gas called argon. We zap it with some electricity to ionize it. And then we use electromagnetic fields to accelerate it out of the thruster in this direction. That pushes pushes our thruster in. We measure how much force this generates, but you put this on a spacecraft and it very efficiently pushes your spacecraft along. So here's another image from the early tests of the thruster. And it had a striking resemblance to the color had a striking resemblance to the plumage of the kōkaku. So we were very happy to be gifted the name of kōkaku for our thruster system. How am I doing for time? But yeah, okay. So I will spend a little bit of time on this. Why is it interesting? So the thruster systems we are developing are a type of electric propulsion for spacecraft. Why that's interesting is because you can the exhaust coming out of your thruster is incredibly fast. It's at least 10 times faster than what comes out of a normal rocket. What that means is that you can have a much larger fraction of your spacecraft that's useful when you want to move around things. So this is indicated by this plot here. On the bottom here, it's showing how quickly you can push the exhaust out of your thruster. And on here is a fraction of your spacecraft that's just your propellant or just your fuel. So for example, for this particular mission profile here, when your change in velocity of your spacecraft is 10 kilometers per second, if your thruster is only doing 10 kilometers per second, exhaust velocity, almost 70% of your spacecraft will have to be fuel. And if you're using not using electric propulsion, then it's closer to 90% of your fuel. So this is the trade. This is why if you want to move your observing satellite or anything along through a high delta V maneuver, you want advanced electric propulsion. And that's what we're developing. The specific type of thruster we use has efficient operation with abundant propellant. It has a high thrust density, and you can vary the exhaust velocity. As I was walking in today, there was somebody was chatting about Starlink, and every single Starlink satellite uses electric propulsion, so it's very common these days. Okay, so just a little bit. These are the components of the thruster that we make. There's you feed in the gas, you ionize it using the thruster here, and then you have the superconducting magnet, a magnet power supply, and a cooler to keep everything cold. Many of these things have been flown in space before. Thank you, Randy, for the slide. I may have seen this before. But of course, what hasn't been flown in space before are the superconducting magnet and the magnet power supply. And thus was born the HECI mission. So this is our technology demonstration to the International Space Station. So we've got a couple of goals with this mission, is to operate a superconducting magnet. The central field, we want to be at least 0.3 Tesla. It's got to work on the station. And we're also hosting some radiation sensors so that we can quantify the effect of the field of radiation to shield radiation. Of course, we face some challenges. I've just listed a couple here because it's on a crewed spacecraft. We need to have a very low stray field, and we also don't want to upset our neighbors. So we're going to occupy this space on the Japanese experiment module, and we don't want our magnetic field to upset the experiments either side of us. So we have to keep quite a low field. The entire thing has quite a low power that we can use, about 100 watts, and we have to manage all of our thermal radiation. So this is roughly what we set out to do. The project has been led by us at Robinson, but we involves it's a New Zealand-wide effort really. Universities and companies across New Zealand. Just a little bit on the name. So it's called HECI, which is the Māori word for egg. Yeah, there's a little bit of kōkako before the egg or egg before the kōkako. And choose which one you want. So, one of the kind of first questions which kind of popped to mind is, well, you have to keep your superconductor cold, but isn't space pretty cold? So, this is one of the first things to, as you approach this, to have a good model of what's actually going on. And the short answer is no. In low Earth orbit, it's definitely not cold enough. You get a lot of thermal radiation coming from the Earth itself. Yeah, we essentially need a cryocooler to keep our superconductor system cold in low Earth orbit. These types of models also, so this type of information also feeds into, when you model the payload itself, you want to take account of how the temperature is going to change over various orbits and how much heat you can expel for the given size. So we spent quite a lot of work putting all of these integrated multi-physics models together to be able to aid in the design of HECI. Just a little kind of bit about how the design finally ended up. So we're kind of occupying two sides of a plate. You can see the one side in this picture here, and another side in this picture here. So we've got a cryocooler. This is the thing which cools a superconductor down to about minus 200 degrees Celsius. It's quite neat. It kind of, you supply it with 50 hertz, it's AC power, and it buzzes away, and in a couple of hours it's down to those really cold temperatures. So it's quite neat. It's a mature technology now. And this is connect. Sorry, I meant to say right at the start of my talk, if anybody has any questions throughout, please, please raise your hand, ask it. I'm more than happy to deal with any questions. On this side of the payload, we have the cryocooler to keep everything cold and all of the electronics to condition the power and control the payload. You can see a photo of how it looked assembled and down in there. And then on the other side, we've got the main part of the experiment, our superconductor magnet. Bettina calls it a steampunk bagel, which I think is a fantastic name. There's a photo of it put together. It is actually about the size of a bagel, this one. One of the things we needed to do was invent a superconducting power supply to energize the magnet. And it's got a very cool name. Not a very useful name, but a cool name, called a flux pump. The other thing to notice is we do have these two radiation sensors, and one far away from the magnet and one closer to the magnet. And this will allow us to do quantitative tests of the radiation shielding concept using magnetic field. So maybe just a few kind of notes about what actually goes on in putting this together. One of the first thing we needed to do was kind of build up the facilities to make and test the hardware. And so we needed a clean space to assemble everything. But for this particular mission, it didn't need to be that clean. So we called it the cleanish room, and we put this up. Of the modeling I've talked about, and making sure that you can do all the simulations of the hardware. And then you also need the spaces to simulate the environment of space. So think there's no air in space. So that matters. That really affects how things get cold and heat gets transported around. So you need these big vacuum chambers. You suck all of the air out of them, and you can put hardware in there to test it. Building up the hardware, the big challenge here is that you can't fix it later. So you have to be very methodical with how the hardware is put together. Here's a photo of Lynn and Zoe assembling. This would be the active side. This is the side with the cryocooler on it. It was very much, a team effort. So you have people working together to, check for errors and so on. And there's also a lot of testing which goes on. So there's kind of a nice little mantra there, test as you fly as you test. So make sure when you're testing your hardware you're testing it in a way you intend to operate it once it's in space. And then once you're in space, don't be tempted to just change that little. You should do it like you tested. We of course had to test for getting to space as well, so vibrations during launch and whatnot. And you know, when something did go wrong, which you have to try and figure out why it was wrong and what you can do to fix the problem. Yeah.
How optimistic were you with regards to redundancy? Like if you're out of like a redundant power supply for it?
No, we don't. Yeah. Not so that comes down to the procedures and the testing. Really, is to make sure you've tested it sufficiently that you're comfortable with its reliability and test it in a way that it's going to be operated once it's the radiation environment is not too bad in low Earth orbit. It's not like if you're going through the Van Allen balance. We did use some kind of nice semiconductor technology, which is supposed to be a bit harder to radiation. Sorry, the first part of your question I've forgotten actually. Redundancy?
Yeah, like redundancy, like if you get like
it's got to be through testing. Yeah. So mission status, it works really well. The system, I'm showing some, you know, a small portion of the data here. So this is over time. This is the magnetic field in the magnets. You know, we said we wanted to get to 0.3 Tesla at least. We can operate at 0.5 or higher. So we're happy with that. But it's, you know, there are lots of other things in making sure it's thermally stable, and we use the you know, we don't draw too much power and all of that sort of stuff. So that was all part of the sort of qualification testing. A big part of the whole mission as well was convincing NASA that we can put our experimental device on the International Space Station. And I think the final safety review was described as being very boring. So I think that's kind of testament to you know, being able to kind of bring them along on the journey and convince them that you know, we're doing everything well and checking off everything that needs to be checked off. So it's now being delivered, and it's basically awaiting assignment for an upcoming cargo mission. And I think that was okay. Yep. So how it looks once we get to the next phase, we shoot up there. It will be unpacked by the astronauts. It then gets installed on this NanoRacks platform, which you see on the outside of the Japanese experiment module. From there, it'll go into the airlock, and then a robot arm will come in and pick it out from the airlock, and then move it out and position it on the outside of the space station. We then get to operate for at least a couple of months. And then one of the really nice things is the whole process gets reversed, or maybe not the launch, but there's a we should get the payload back and have a chance to have the space hardware in our lab again. So that will be pretty exciting. And that's all I wanted to say. So yeah, thanks so much again for the opportunity, for the time. I'm really happy to take any questions.